all, I'm going to introduce what welding is. Welding is a process that joins metals by applying heat to form a strong bond. Two commonly used arc welding methods are gas metal arc welding (GMAW) and gas tungsten arc welding (GTAW). GMAW uses a consumable wire electrode and shielding gas to protect the weld pool. In contrast, GTAW uses a non-consumable tungsten electrode and produces clean, highly quality welds with excellent control, ideal for thin or non-ferrous metals. Although both use shielding gases like argon, they differ in their equipment, techniques, and applications. So, this is the example for GMAW and GTAW welding. So now, I will explain gas metal arc welding. The method is use a consumable wire electrode that continuously feeds through a welding gun. The arc forms between the wire and the workpiece, melting both to create the weld pool. For the machine, it includes a power source, wire feed system, welding gun, and a gas cylinder. For the shielding gas, common gases, argon, or a mix, protect the molten weld from atmospheric contamination. For the electrode, the wire electrode acts as both scalar and conductor. And now, for the GTAW, gas tungsten arc welding, the method is use a non-consumable tungsten electrode to create the arc. A separate filler rod can be added manually if needed. For the machine, it consists of a constant current power source, PID torch, foot pedal to control current, and a gas cylinder. Shielding gas, pure argon or helium, or a mix used to shield the weld area. Lastly, the electrode, tungsten electrode, non-consumable available in several types. For example, like pure tungsten and thoriated.
Next, I would like to talk about the type of currents and polarity used in gas metal arc welding and gas tungsten arc welding. For the gas metal arc welding, the type of current is direct current electrode positive (DCEP). The polarity effects are electrons flow from workpiece to electrode. Next, the more heat on the workpiece, the deeper the penetration will be produced. The direct current electric negative gives shallow welds, and this method is best for steel and general fabrication. For gas tungsten arc welding, the type of currents are direct current electrode negative, direct current electrode positive, or alternative current. For the polarity effects are direct current electrode negative gives deep penetration for steel and it is stainless. For direct current electrode positive, it gives cleaning action. It can remove oxides. For alternative current, it gives balance, cleaning, and penetration. These methods are the best for aluminum and non-ferrous metals. Next, I would like to talk about the advantages and disadvantages of gas metal arc welding and gas tungsten arc welding. The advantages of gas metal arc welding are it has high deposition rate, continuous wire feed, cleaner weld, easily automated, and good for thin and medium materials. While the disadvantages are it requires shielding gas, it has higher setup costs, it is limited to flat and horizontal positions for best quality, and it less suitable for very thick materials. While the advantages for gas tungsten arc welding are it produces high quality and precise welds, it has no slag and giving a clean appearance, it can weld thin materials and non-ferrous metals, it is also a stable arc and has an excellent penetration control, and it allows use of filler rod or autogenous. While the disadvantages are it is a slower process, it requires high operator skill and training, it is more expensive for equipment and shielding gas, and it is not suitable for outdoors. Next, I would like to make the comparison between gas tungsten arc welding and gas metal arc welding with the other welding methods. Compared to shielded metal arc welding, the gas tungsten arc welding gives better precision and weld quality, but it is slower. While compared to gas metal arc welding, gas tungsten arc welding is cleaner and more precise but less productive.
For my part, I will present the most common types of welding defects, explain what causes them, and share practical strategies to prevent them. Let's begin with porosity, which refer to gas pockets or void formed in the weld due to trapped gases. This can weaken the weld and lead to failure under stress. Cracks are another serious defect, often caused by stress or poor technique and improper cooling, and they can appear in or near the weld or base metal. Undercut occur when a groove is melted into the base metal adjacent to weld toe but left unfilled, reducing the cross-sectional area and weakening the joint. Incomplete fusions happens when the weld metal fails to bond properly with the base metal, while incomplete penetrations means the weld metal doesn't extend through the full thickness of joint. Slack inclusions involve non-metallic material getting trapped in the weld, which can create a weak spot. Spatter refer to small metal droplets scattered around the weld area, which may not affect strength but can impact appearance and require cleanup. Overlap occur when the weld metal flows over the base metal without bonding, and distortion is the warping of metal caused by uneven heatings and cooling during the welding process. To prevent these defects, several strategies can be applied. For porosity, it's important to use clean base material, proper shedding gas, and dry electrodes, while avoiding moisture and contaminants. Cracks can be minimized by preheating thicker material, controlling the cooling rate, use appropriate filler material, and reducing stress. To avoid undercut, welders should adjust the travel speed and angle and avoid excessive heat input. Incomplete fusion can be prevented by ensuring correct electrode angle and amperage settings and avoiding excessive travel speed. Incomplete penetration requires a correct joint design, increased heat input if necessary, proper welding parameters, and including root opening. Slack inclusion can be avoided by cleaning the weld area between passes and use correct welding technique.
For my parts, I will present 5 types of distortion in welding. Number 1 is longitudinal distortion, transverse distortion, angular distortion, buckling distortion, and last but not least is rotational distortion. How to minimize each type of distortion. Longitudinal distortion happens when the weld mantle and the base mantle expand and contract unevenly along the direction of the weld. As the mantle cools, the weld area shrinks more than the surrounding base material, causing the workpiece to bend or bow lengthwise. To minimize this type of distortion, balanced welding should be practiced. That means welding from both sides of the joint whenever possible so the shrinkage force cancel each other out. Reducing heat input is also important. By controlling welding parameters such as current voltage and treble speed, the amount of thermal stress can be reduced. Using clamps, jigs or strong backs to hold parts securely during welding can also help prevent the mantle from moving or bending as it cools. Presetting or pre-bending the plates in the opposite direction of expected distortion can further ensure alignment after welding. For number 2 is transverse distortion. We can use tack welds, proper fixtures, and symmetrical welding. Transverse distortion occurs across the width of the joint when the weld shrinks in a direction perpendicular to the weld line. This usually causes the plates to pull together or move apart after cooling. To control this, tack welds can be placed at regular intervals before final welding to hold the plates in correct alignment. The use of proper fixtures, such as jigs or rigid supports, can also help maintain the correct spacing and prevent side movement during the process. Performing symmetrical welding, for example, welding alternate on both sides of a central axis, distributes heat more evenly, reducing the concentration of stress on one side. Adjusting welding parameters to lower heat input and using smaller bends can further reduce the amount of transverse shrinkage. For number 3 is angular distortion. We can use double-sided joints, reduce heat input, and apply backstep welding. Angular distortion happens when one side of the weld joint expands and contracts more than the other, causing the plates to form an angle after welding. This is especially common in single-sided welds because all the heat and shrinkage are concentrated on one side. To minimize it, welders can use double V or W joint preparation, which balance the weld metal and heat on both sides of the joint, producing even shrinkage. Reducing excessive heat input by adjusting the welding current, voltage, and travel speed can also prevent uneven thermal stress. Another effective method is backstep welding, where short welds are made in the opposite direction of progress, allowing each section to cool before the next one begins. This helps to counterattack angular pull and maintain the proper joint angle. Number 4 is buckling distortion. We can use smaller weld passes, stiffeners, and preset parts. Buckling distortion mainly occurs in thin plates or large plate surfaces when compressive stress from uneven heating causes the metal to wrap or wrinkle. Since thin materials are more flexible, they deform easily when excessive heat is applied. To prevent this, smaller weld passes should be used instead of large, continuous weld, which produce more heat and stress. Adding stiffeners, ribs, or braces temporarily during welding can help keep the plate rigid and prevent buckling. Presetting or slightly bending the material in the opposite direction before welding can also help balance the final stress once the weld cools. Additionally, using terminate welding instead of continuous welds where possible helps to reduce overall heat input and minimize wrapping. Last but not least is rotational distortion. We can apply proper welding sequence, preheat if needed, and for certain materials, preheating can be used to lower the temperature difference between the weld and unweld zones, thereby reducing stress. Welding alternately on opposite sides of the structure and using symmetrical weld layouts are also effective in preventing rotational distortion. In conclusion, gas metal arc welding, which is GMAW, and gas tungsten arc welding, GTAW, are both important and efficient welding methods. GMAW is faster, easier to use, and suitable for thick materials and large-scale production. In contrast, GTAW offers greater precision and cleaner welds, making it ideal for thin or high-quality works such as stainless steel and aerospace components. While GMAW focused on speed and efficiency, GTAW emphasized accuracy and weld quality, and both play vital roles in modern metal fabrication. That's all from us. Thank you.